Good day, viewers. Welcome back to class. In today's physics class, we'll be talking about simple harmonic motion. Mind you, this class is brought to you by the O3 School app. The app is based on solving problems on JAMB and WAEC. Mind you, also, the app is completely available in Play Stores and Apple Store, free to download. And after downloading, do well to also activate. All right, so let's kick start. We said what we have on the board is simple harmonic motion. When you hear the word harmonic, that means there is presence of vibration. And when there is presence of vibration, that means there is presence of frequency. Then you talk about motion. Motion, you talk about movement. There's a movement with respect to time. That means there's a change in position of an object in respect to what? To time. So that means that when you talk about harmonic, there is a presence of an alternating quantity in such motion, and which is the frequency. So frequency alternates. So because frequency is a variable quantity, it varies with time. That's why we said simple harmonic motion. Now, what is simple harmonic motion? Simple harmonic motion is just when a body is the movement of a body by means of restoring force. If the restoring force is directly proportional to displacement, such body has undergoes simple harmonic motion. A good example is your simple pendulum. A simple pendulum. Simple pendulum has a restoring what? Force, because the motion of the simple pendulum bob is going back and forth. The back and forth means to and fro. And when you hear the word to and fro, what comes to your mind is oscillatory motion. In our previous video, we talked about the types of motion. So oscillatory motion, we can also classify the simple harmonic motion as an oscillatory motion. The only difference is that the simple harmonic motion is of two kinds, is of two types or kinds. We have the linear simple harmonic motion and the angular simple harmonic motion. When you hear the word linear simple harmonic motion, what comes to your mind is that it means the motion takes place on a straight line, Then when you hear the word angular, angular means is moving in a what? In a circular path. It's moving in a circular path around the circumference of a circle. Now, we said again that one thing you need to know about simple harmonic motion is that for a linear case, the restoring force is directly proportional to the displacement. Also, the acceleration formed by that motion is always directly proportional to the displacement. For example, what we have here, we have a linear simple harmonic motion. This is a spring. You have a spring and you have a block, or you have a wood. Now, these springs undergoes Hooke's law. Well, if you could recall from elasticity, elasticity is just the ability of a material to regain its position or size after being stretched. You are regaining your size after being stretched or after some kind of a deformation. We are made to understand from Hooke's law that the force applied to a string is directly proportional to the extension produced. But in this case, we are not basing more on the Hooke's law. What we just want to know here is that if we try to move this block, the spring will extend. There will be an increase in length. So what does that tell us? The more force we applied to this block, the more the extension. Now, when the force is removed, what happens? The spring comes back to equilibrium. Equilibrium means it comes back to its state of rest. At that point, the distance becomes zero. Now, when distance becomes zero, it's as a result of the fact that the restoring force is zero. What is the meaning of restoring force? Restoring force is just the force that attempts to pull the spring back to its original position. Back to its original position. Now, immediately the spring, if immediately you extend the block, the spring elongates. When the spring elongates, the distance also increases. So that's why we say the force is directly proportional to the what? To the distance. The more the restoring force, the more the distance. The more you also the more you reduce the restoring force, the displacement or the distance also reduces. Now, there is a negative here because the restoring force is opposite the displacement. The reason is because the acceleration is opposite the displacement. The acceleration always opposes the displacement. All right. Now, coming here also, we have a linear movement. This is a simple pendulum. Now, we have a bulb here. This bulb, when there is an applied force on this bulb, what happens is that the bulb swing. It swings left and right. Now, by the time the bulb swing left and right, there is energy changes. Energy changes from kinetic energy to potential energy, or from potential energy to kinetic energy. In most popular JAMB questions, the question will be asked, here may be 0.1 or 0.2 or 0.3. If here is 0.1, most question that will be demand from you from JAMB is, where do you have the maximum kinetic energy? The maximum kinetic energy is at this point. Because at this point, what happens? The potential energy is zero. So here you have potential energy. The kinetic energy at this point is zero, while the potential energy here is maximum. So the bulb swing, you see it's swinging to and fro, back and forth. So it's moving to and fro. Is a good example of simple harmonic motion. Then we also have applications, oscillation in electric circuit. Oscillation in electric circuit. In generation of radio frequency, what happens? The quantity, they undergo what? Vibrations and oscillation. We have swinging of cradle, vibration of turning a fork. Vibration of turning fork also cause simple harmonic motion. So in this video, we are made to understand that there is a restoring force acting on a body, setting that body to displace in the sense that, as I've earlier said, consider this string. By the time you drag, there's an applied force dragging this block. What happens is that the spring elongates. And by the time the spring elongates, the restoring force is directly proportional to the distance at which the spring elongates. Now, what comes to our mind is that during vibration, there is a sine wave that is formed. As a result of the oscillation, sinusoidal waves are formed. So let's see. You have sinusoidal waves. Now, sinusoidal wave is formed. As a result of the vibrations, you have sine wave. So what happens is that there is frequency, because frequency is the number of cycles per seconds. So you have an amplitude. There's an amplitude. You have sinusoidal wave, sine wave, sine or cosine waveforms. Wave is forms. Whereby you have your y equals to the displacement is a sine omega t. Now, your displacement is a sine omega t, or your x is also a sine omega t. Okay? So if we have that, yeah, this is displacement. This is displacement. The A there is amplitude. Is amplitude. And the T there is time. Time in seconds. Time in seconds. And omega there is the angular. Omega there is the angular speed. And this angular speed is in radian per seconds. So what you have as a result of the vibration of the vibrating fork or the spring, it leads to what? Sine wave. There's a sinusoidal waveform. In the application, I also told you about is using an electric circuit in generating radio frequency. Maybe in relation to electricity, we can have instantaneous current is I mass sine omega t. Instantaneous voltage, E mass, sine what? Omega t. So they also have practical application in electricity. Okay. Now, there's also a relationship between period, omega is 2 pi f, then frequency is 1 over t. So we need to be conversant with some terms, some terminologies. Now, A is the amplitude. Amplitude is the maximum displacement of that oscillating body from the point of equilibrium. The alternating or the oscillating body from what? From rest position. If it's a wave particles, for instance, would have said, okay, the maximum displacement of wave particles from rest. But now we're not talking about the wave particle itself. We are talking about an oscillating body. Now, as the body oscillates, it generates somewhat some harmonics. Now, because of the presence of harmonics, cycles are formed. So in the presence of the cycle, the movement of the particle around the cycle creates what we call an angular speed of that particle. So angular speed in radian per second is 2 pi f. And frequency is 1 over period. Okay, so mathematically, we can also equally say that angular speed is 2 pi over t because omega is 2 pi f. And what is frequency? Now, we have, during the course of this motion, we may have incessant or reoccurrence of vibrations. So the numbers of vibrations per unit time give rise to frequency. Give rise to the frequency. Now, the time taken to complete one cycle is what we have as the period. It's what we have as the period. Okay. So I brought about this sinusoidal wave because I told you the movement of the spring under the linear simple harmonic motion. I said the linear movement of the spring is as a result of the fact that the restoring force is directly proportional to what? To the displacement. And the acceleration, by the time the block moves, the block exerts some acceleration. And that acceleration is always directly to the what? The displacement from the mean point. From the main point. Now, what is the main point? Let me draw the block again. From the main point. The main point, you have, let's say this is the block. I have something like this. And this is the block. Let's say here is the main point. The main point is the half of the elongation. The half of the elongation is where you have the main point. At this point where the string is tied, or the spring rather is tied, is your point of equilibrium. Your point of equilibrium, that's the rest position. Now, in the absence of restoring force, the distance is 0. When the restoring force is 0, that means F is 0, displacement will also be 0. There is no force. Now, when displacement is 0, what comes to your mind also? Acceleration will be 0. Acceleration will be 0. Remember from Sir Isaac Newton from second law, we said F equals to MA. So when force is 0, there is no force that is being applied. No matter how the object has a mass of 1,000 grams, there will be no movement because there's no force. Setting the mass of this body to move. So in the absence of force, definitely acceleration will also be 0. All right. Now let's talk more on the restoring force. The restoring force on this spring. Now, in angular simple harmonic motion, we talk about torque because torque takes place in a rotation. You have torque in a rotational body. While for a linear body, you talk about force. So what I've been saying so far, I'm concentrating more on the linear simple harmonic motion. So let's talk more about the restoring force. Okay, the restoring force. Now, why do we say restoring force? Restoring force simply means the force that tends to move the spring back to its original position. That's the restoring force. So we are made to understand that the restoring force is directly proportional to what? To the displacement. So if that is directly proportional to the displacement, that means that F is equals to minus Kx, where K is a constant. And why do we say it's a constant? Because the spring might be made up of different material. What happens if the spring is made up of copper, is made up of aluminum? So this material, they have different properties. So there's a spring constant, which is K. We call it spring constant. Now, if F equals to Kx, from second law of motion, we know that F is equals to what? Ma. Now, if F equals to Ma, definitely Ma is equals to minus what? Minus Ks. Now, Ma equals to minus Ks. Now, if Ma equals to minus Ks, from equation of motion, we also know that acceleration is equals to what? dv dt. Acceleration is what? dv dt. That is change in what? Velocity over change in time. Now, velocity also is what? dx dt. Velocity is what? dx dt. What is dx dt? That means change in displacement over what? Change in time. Now, what brought about the acceleration? Because there was a movement of the block from the previous, from the block I drew, the block and the spring. There's a movement of the block which causes the elongation in the spring. So definitely there is a movement. Since there is a movement, there is a change in displacement per unit time. So change in displacement per unit time give rise to what? Velocity. Now, change in velocity per unit time will also give rise to what? Acceleration. So definitely we can take the square of the displacement over the square of the time, giving rise to what? Acceleration. So since v equals to dx dt, definitely we can have d square x dt square in the second order. Second order means in the second derivative. So conclusively, we can say acceleration is d square x dt square. Okay, so now we can come back and let's say this is equation 1 and this is equation 2. So put equation 2, put equation 2 into equation 1. Now, putting equation 2 into equation 1. Equation 1 says MA. So where we have A, we put the value of what? D square S, the T square. So we have M, D square X, the T square, okay, equals to minus KX. We can divide both sides by M. So we have M, which is the mass, M, over what? Over N. So we now have D square X, the T square, equals to minus KX over what? Over N. D square X over the T square. This minus, if it's crossing the equality sign, change to plus. So we have plus KX over M equals to what? 0. This is a second order equation. Second order what? Equation, showing that the acceleration is also directly to the displacement. And the acceleration is always opposite the displacement in a linear simple what? Harmonic motion. You may be asked to derive or show that the acceleration obtained by a body undergoing simple harmonic motion is directly proportional to the displacement from a what? From the mean point. So this is what you have. Okay, we can still break it further. To break it further, mathematics, to break it further, we can have okay, d square x, d square x, the t square plus omega square x. Omega square x equals to 0. So where omega square is k over m. So that means the square of the angular velocity. The square of the angular velocity is the force constant over the mass. So let's go. We know that d square x over the t square is a. So definitely this is a plus omega square s equals to 0. So a is equals to minus omega square x. So you can see, if you see the pointed arrow now, it shows that the acceleration is directly proportional to what? To the negative of the displacement. So acceleration is equals to minus omega square what? Omega square x. All right. Okay, let's see some problems. Let's solve some problems and some formulas to be noted. Now we have a question here. It says, 1, a particle number of what? Oscillations per time. Per time. So what's the number of oscillations? The number of oscillations is given 20. You make 20 oscillations. So we have 20 and the time is 5. So definitely we have 4.0 or 4 hence. So mind you, frequency is the number of oscillations per unit time and is measured in hence. Now B says we should find the period. Period is the inverse of what? Frequency. So period is T, and T is 1 over F. So definitely you have 1 over 4. 1 over 4, you have 0.25 seconds. 1 over 4 is 0.25 seconds. So that means that at 4 hands, we have 0.25 what? Seconds. Okay. Then we also have a problem from JAMB. Problem from JAMB 2019, question 42. Goes this way. It's a diagram rather. Okay. We have a bulb, a bulb, a bulb, and a bulb. 1, 2, 3, 4. So the question from 2019, it said, at what point is the kinetic energy? At what point is the kinetic energy maximum? At what point is the kinetic energy maximum? In the past video I drew, we saw where kinetic energy is what? Is maximum. Here you have higher potential energy. Point 3, you have higher potential energy. At point 4, you have higher potential energy. So the only point you have is at the vertical. At the what? Equivalent length, or at the vertical. At point 2, that is when you have the maximum kinetic energy. So the answer is point 2. At point 2, you have the maximum potential length, the maximum kinetic energy. So the maximum kinetic energy is at point 2. Okay. Yes, as I've earlier said, I said a body is said to be in a linear simple harmonic motion when it moves to and fro about or along a straight line. That is a linear simple harmonic motion. But if the body is moving around the circumference of a circle or around its axis, if it's moving around its axis, that means it's performing angular simple harmonic motion. A good example is your work clock. The seconds, the minute hand, they are moving around in circles, in its axis, moving around its axis. So that is angular. The restoring force at that point is the torque, because it's moving around a point, angle at a point. So you talk about the torque. Okay, then the restoring force, the force that brings the oscillation object back to equilibrium position. I've said it before. That's also the restoring force. Okay, now let's also talk about, in that spring, the spring has an elastic potential energy. We're made to understand that from Hooke's law, because Hooke's law talks more on the force applied to a spring. Now, the total energy is 1/2 kx squared. The force constant times the elongation in form of the displacement. That will give us the total energy. All right, so let's see more problems from WAEC and JAMB. Okay. Okay, let's see question from, this is a question from 2013. Okay. All right. Let's see. Problems. Okay, let's say 2021, question 13, rather. A particle vibrates with simple harmonic motion. A particle vibrates with simple harmonic motion. Simple harmonic motion, if its acceleration is 25 times its displacement. Yes, this one tally with the acceleration derivation we did just now. It says a particle vibrates with simple harmonic motion if its acceleration is 25 times its displacement. Now, what do we have? We know that acceleration is minus omega square what? X. Yes. And acceleration is always directly proportional to what? To the displacement. Now, I said if the acceleration in meter per second is 25 times its displacement. So that means this is acceleration is 25 times its displacement. A is the acceleration, X is the displacement. So acceleration, when you hear the word is, we know we have equals to. In mathematics, is equals to. Now the acceleration is 25 times the displacement. Now acceleration is what? 25 times is what? Displacement. So definitely we can say, okay, acceleration is omega square x. Let's omit the negative. Now, what is acceleration? Acceleration is 25 times the displacement. So that means we have 25x omega square x. So s can cancel x. Omega square is 25. Omega square is what? Plus or minus square root of what? 25. So omega is 5 radian per second. 5 radian per second. Because the question says a particle vibrates with simple harmonic motion if its acceleration in meter, the acceleration is in meter per second square, is 25 times its displacement in meters. Find the period of the motion in terms of pi. Find the period. How do you find? They say find the period in terms of pi. What will come to your mind in terms of pi? Okay. Now we have what? What is the relationship? Relationship is that omega is 2 pi f. Omega is 2 pi f. Omega is 2 pi f. We are told to find the period in terms of pi. So frequency is 1 over what? 1 over period. So where I have frequency, I'll have 1 over period. So omega is 2 pi f. F is frequency, which is 1 over t. Definitely times 1 over what? Over t. The question says we should find the period in terms of pi. Therefore, you just cross multiply. So omega times t, I can decide to say, okay, t is equals to 2 pi what? Omega. 2 pi omega. So 2 pi, omega is what? 5. So you pick 5. So the time is 2 over 5 pi seconds. So let's see the options. The options. Okay, 2 pi over 5. That's roughly 0.4. 2 over 5 is 0.4. So t is 0.4 pi seconds. So the options there, let's see the options, is D. So the answer there is what? Is D. So what you do, you need to know the relationship between these parameters. Majorly, what's the relationship between frequency and what? And period. So it's just a reciprocal. It's an inverse. So frequency is the inverse of period. And what is omega? Omega is 2 pi f. So we can now replace f by 1 over what? Over period. So that's how the answer comes. So you have 0.4 pi seconds. Okay, let's see another one. Another question. And this one says a pendulum bob. We have 2 seconds, 0.83, 0.08, 0.60. Okay. Now the question says we should find what? Now they say calculate the period of the motion. How do you get period? They said a simple pendulum executing a simple harmonic has 2 centimeters and 12 hands as the amplitude. So there's an amplitude, you have amplitude, and you have the frequency. Amplitude is the maximum displacement of that particle performing simple harmonic motion. Now, how do you get frequency? Just what I said before. Frequency is the inverse of time. Inverse of period. So you have period will be 1 over frequency. So you have 1 over 12. 1 over 12, you have 0.08 seconds. So 1 over 12, you have 0.08 seconds. So the option there is C. So try as much as possible to understand the relationship between frequency and period before you can even solve complex problems. Okay, now let's go more deeper. Now, what comes to your mind is the velocity and the acceleration, the velocity and the acceleration of the object at any time t. That is the instantaneous velocity. The instantaneous velocity or the instantaneous acceleration at any time t. So now let's come back. An object executes a simple harmonic motion whose displacement x varies with time according to the relation. According to the relation, x equals to 5 sine 2 pi t minus pi over 2, where x is in centimeters and t is in seconds. Determine A, the amplitude, frequency, period, and the phase constant. All right. Now, what we need to do first is to get the amplitude. A, amplitude. Amplitude. Now, how do you get amplitude? This is the amplitude. Amplitude is the maximum displacement of the simple harmonic of the body performing the periodic motion from rest. So that is 5 centimeters. The amplitude is just 5 centimeters. You don't even need to solve. Mainly looking it at the equation. This is the harmonic side. This is the phase constant side, because due to the vibration, there is a sine wave. So this is what you have as a sine wave. The sine wave is an alternating quantity. It's alternating and it's changing with time. The quantity is changing with time. So the amplitude is 5 centimeters. Then let's say this is A1, AII. The next one says we should find frequency. How do you get frequency? We know that omega will be 2 pi t. Omega is 2 pi t. So omega is also 2 pi f equals to 2 pi t. Now, since omega is 2 pi t and we have 2 pi f, so definitely, okay. The amplitude, the frequency, the period, and the phase constant. So we have 2 pi f. 2 pi f is equals to 2 pi t. So we can have 2 pi ft. 2 pi ft equals to 2 pi f. So definitely 2 pi we cancel. 2 pi will also cancel. So our f is 1.0 Hz. So the frequency is 1.0 Hz. Now you have 1.0 Hz. What will equally be the period? Period is just 1 over frequency. So since period is 1 over frequency, I period is 1 over frequency. So period is 1 over 1. We also have 1 second. So period is also 1 second. Now the next thing is to get the velocity. The next thing is to get the velocity. Okay. Now we're made to understand that x is 5 sine 2 pi t, right? 2 pi t minus pi over 2. Okay, we can equally get the phase constant. The phase constant is 5. Sorry, I4. Phase constant is pi over 2 radian. Phi is what? Pi over 2 radian. Because it's in the form of y equals to a sine omega t plus minus phi. So here the phi, or the phase angle, is pi over 2. Omega t is what you have as 2 pi t. A sine, your A is 5. That was why the amplitude was 5. So A is what? Is 5. Now our major concern is to get the velocity. Velocity is in the first order differential, while acceleration is in the second order differential. So V is equals to dx dt. V is equals to what? Dx dt. Now, we have a displacement equation. The displacement equation, x is equals to 5 sine 2 pi t minus pi over 2. So for us to get velocity, we differentiate with respect to time. You must be conversant with your calculus, because sometimes these alternating quantities, they changes at any time. When alternating quantity changes at any time, it becomes instantaneous. It becomes instantaneous values. So now let's differentiate with respect to x. So we now have equals to d dx, sorry, this is t, because velocity is changing displacement over time. So d dx over dt equals to d dt of the entire function, which is 5 sine bracket open 2 pi t minus pi over what? Over 2. So that's what you have. Now, if we differentiate, what do we have? What do we have? We have V equals to d dt of 5 sine into 2 pi t minus pi over what? Over 2. All right. So we have 5 here is a constant, and we have sine 2 pi t. Now, if you differentiate sine 2 pi t, we'll have So V, let me change this. It's just like differentiating. If I say, okay, for example, y equals to sine 2x. If I differentiate this, I'll have what? Dy dx. I'll have dy dx. If you differentiate sine, you have cos. So I'll have 2 cos 2x. So definitely for this, I'll have my velocity is d dt of this. I'm going to have 5 times 2 pi times 2 pi sine. Sorry, if you differentiate sine, you have cos. So 5 times 2 pi cos, I'll have 2 pi t minus pi over what? Over 2. So definitely my V becomes 5 times 2. We have 10. So 5 times 2. 5 times 2, you have 10. So 10 pi, you have 10 pi cos 2 pi t minus pi over 2 centimeter per seconds. So that will be our what? Our velocity. So the velocity is what? 10 pi cos 2 pi t minus pi over 2. Where pi over 2 is the phase constant or the phase angle. While 2 pi t is the angular speed. The 10 pi there can tell us, the 10 pi there is what? Is the amplitude. So the 10 pi there is the amplitude. The amplitude is the maximum displacement of the object undergoing periodic motion from the point of equilibrium, from the point of rest. So this is our what? Is our velocity. Okay. And the next thing is to get what? Acceleration. When you have velocity, you can get acceleration. Because the differential of velocity per unit time give rise to what? Acceleration. So let's solve that of acceleration. For acceleration, we differentiate velocity. All right, now, velocity, point B, I now. Velocity, we got velocity to be what? 10 pi sine into 10 pi, cos into 2 pi t minus pi over 2. This is what we got as velocity. So acceleration is dv dt. Acceleration is dv dt. So what do we now have? We have d dt into 10 pi cos into 2 pi t minus pi over 2. So this is what we have. So we need to differentiate with respect to what? Time. If you differentiate cos, what do you have? Okay, you have what? You have minus. So that means acceleration is d dt of 10 pi cos what? 2 pi t minus pi over what? Over 2. All right. So now acceleration becomes, when you differentiate cos, you have minus. But we have 2 pi here, so it becomes minus 10 pi times 2 pi. The minus is coming because if you differentiate cos, you have a negative sign. So we have sine bracket 2 pi t minus pi over what? over 2. That is sine function. So acceleration becomes minus 20 pi square sine 2 pi t minus pi over what? Over 2. Minus 20 pi square sine what? 2 pi t minus pi over 2. And that value will be in what? Acceleration is in what? We have meter. No, the value here is in centimeter second square. Because it was not given in meter. The velocity was given in centimeter per second. So we also have centimeter per second square. So this is the acceleration produced by such displacement waveform. So, all right, let's take one more question. All right. For simple pendulum, this marker. For simple pendulum, T is 2 pi root L over G. So this is the bulb. The weight of the bulb is acting downward, and M is mg equals to weight. I have parallel force and perpendicular. All right. The weight component of the bulb has two components, one parallel and one parallel to the plane, and one is perpendicular. Perpendicular is mg cos theta and mg sin theta. Then we have a rigid body, or you call it a rigid support. Rigid support. Then the movement of the bulb to and fro generates an angle theta. This angle theta is the angular displacement. Angular displacement. As I've earlier said before, there are energy transformation in this form, from potential energy to kinetic energy and kinetic energy, because this is a mechanical system. For a mechanical system, you talk about mechanical energy in form of kinetic and potential. So you have, as I've earlier said, at this point, you have the maximum kinetic energy. At the point of equilibrium, you have the maximum kinetic energy. While at this point, you have the maximum potential energy, because the bulb comes to rest in some nanoseconds or milliseconds before moving to and fro. Now, at this point, you have zero kinetic energy, maximum potential energy. Now, the period of a simple harmonic motion, the period is the period is 2 pi square root of L over G. Here, L is the length of the string, or if you're using a rope, either rope or string. Then you have G. G is gravity, because the mass of the bulb is under the influence of gravity. the weight of everybody is acting downward. Okay. So let's see some examples. Let's see some examples relating to that. Now, from 2027, let's see JAMB 2017. The major thing now is, how do you apply all these formulas? How do you apply them, the applications? So let's see. JAMB. We have JAMB 2017. 2017. Question 23. Wow. A simple pendulum makes 90 oscillations in 1 minute. 20 what? Oscillations. So it makes 90 oscillations in 1 minute on the Earth's surface. Now, the number of oscillations per minute which the same pendulum will execute at an altitude where the acceleration due to gravity is 81% of its value on Earth. So what does that mean? Here, you are above the Earth now. If you are above the Earth, in our previous video, I told you there's what we call weightlessness. Weightlessness. That means when you are above the Earth, the body becomes weightless because the value of gravity becomes very negligible, very small. But when you are close to the Earth, you have more gravity, close to 10 meters per second squared. Okay. So therefore, now, period is 2 pi root L over G. Now, we are giving numbers of circle. Number of oscillation per time is frequency. The number of cycles or the number of oscillations, number of vibration per time give rise to frequency. So in this formula for a period of a simple pendulum, we don't have frequency. So we create a relationship. We know that, okay, we know that frequency is 1 over what? Frequency is 1 over what? Period. So definitely we have period to be 1 over what? Frequency. Okay, hence, we can say that 1 over F is equals to 2 pi root L over G. Okay? 1 over F equals to 2 pi root L over G. We can take the square of both sides. If we take the square of both sides, we can have 1 square F square, 2 square pi square times L over what? Over G. So definitely we can have, this is also equal, it implies that 1 square is 1. So we have 1 over F square is equals to 4 pi square L over what? Over G. Which implies if I need to make F squared the subject of the formula. So I have F square 4 pi square L is equals to G, because 1 times G is G. So what do I have? So remember, I have L over G. So I have what? F squared is equals to G over L times 1 over 4 pi square. Okay? That's the relationship. Now, we are looking for frequency and not the square of frequency. So we can clean this. We are looking for what? We are looking for frequency, not the square of frequency. So we can now take the square root of both sides. So we now have F equals to what? The square root of G over L times 1 over 2 pi. So indirectly, we can have 1 over 2 pi G over what? Over L. So this is the formula we have to apply. So back to the question. A simple pendulum makes 90 oscillations in 1 minute on the Earth's surface. Now the number of oscillations per minute which the simple pendulum will execute at an altitude where the acceleration due to gravity is 91% of its value on Earth. So that means we can say F1 equals to 1 over 2 pi root G over what? Over L on Earth. This is on Earth. Then F2 will be 1 over 2 pi root. Now, 0 point. Remember they said what? Let's see. He said we execute an altitude where the acceleration due to gravity is 81% of its value on Earth. If the value on Earth is, let's say the value on Earth is 9.8. 9.8. Now that means 81% of 9.8. So what do we have? So 1 over 2 pi equals to the square root of what? 0.81 of the gravity on Earth. So it is over L. So we have F1 equals to this and F2 equals to this. So now we can divide equation 1 by equation 2. We divide equation 1 by equation 2. 1 over 2 pi will go. 1 over 2 pi will also go. And square root will equally go. Our length will equally go. The G will equally go. We'll be left with F2. F2 is equals to what? 0.9 F1. Why? Because it said a simple pendulum makes 90 oscillations in 1 minute. And in 1 minute, you have how many seconds? In 1 minute, you have 60 seconds. Now let's make some hints. Number of oscillation per time will give us what? Frequency. Number of oscillation per time, you have what? Frequency. Because frequency is number of oscillation per time. So in that case, we have oscillation. Now F2 is 0.9 times 90, which is equals to 81 oscillations per minute. So let's see. We have F1 equals to 1 over 2 pi root G over L. And F2 equals to 1 over 2 pi root 0.81. Because when the what the question says is that the number of oscillation per minute which the same pendulum will execute above the Earth's surface, where the acceleration due to gravity is 81% of its value. So what we are taking 81%, that's 0.81 of the entire what? G. For example, if G is 10, we are taking 81% of G. If it's 50%, would have been 50% of G. Okay, so the next thing is F2 is 0.9 times what? F1. Now, F1 is the first frequency during the oscillation, and F2 is the second oscillation. Now, this F2 is equals to 0.9 times F1. So F2 is 0.9 times F1. F1 makes what? 90 oscillations in one minute. So F1 is just what? 90 over 1. So you have 90. So therefore, F2 is 0.9 times 90. So if you check your options, F2, you have 81 per minute. So which of the option is there? A is 73, B is 81, C is 100. So you have 81 81s. Let's make a recap again. A simple pendulum makes 90 oscillations in 1 minute. How do you get the frequency? The frequency is number of oscillation per time. So we have 90 over 1. That one is certain. Now the next thing is that the number of oscillation per minute which the same pendulum will execute. That means you are looking for a new frequency now. The first frequency is 90. Now that means, what does that mean? It means that at 90 oscillations, the number of oscillation per time is 90. And that is also equals to F1. F1 is frequency, and frequency is number of oscillation per time. So you have 90 over 1 because it was just in 1 minute. Per minute, number of oscillation per minute, you have 90. So if we are to use the pendulum formula, F equals to root 2 pi, or T equals to 2 pi root L over G. Now, because we don't have period, we are relating it with frequency. It's just the reciprocal. So F1 becomes 1 over 2 pi root G over L. So what's the next thing? The next thing says that if 81% of the entire gravity is used, compare that. Now, you are talking about altitude. Now, you are above a certain part of the earth, above the earth. Maybe let's say you are above the earth by 400 meters away or 900 kilometers away, for example. Now, 0.81 of what? Of G. So let's see if we can cancel some things out. Okay. I'm just trying to see how we can explain further. We have F equals to 1 over 2 pi root L over G. Yes, root G over L. Then this is F1. Then F2, 1 over 2 pi root 0.81 G over L. Because point 2 says we are taking 81% of G. And 81%, that's 81 over 100 of G. And that's where we have 0.81 G. So let's divide. If you say F1 over F2 is equals to this, we cancel out. Okay? 1 over 2 pi, 1 over 2 pi, they all cancel out. Then square root will also cancel square root. What do we have left? We have G over L divided by 0.81 G over L. So F1 over F2 is equals to G over L times L over 0.81 G. So what do you observe now? G will cancel G. I'm trying to break it down now. G will cancel G. L will cancel what? N. Now we are looking for F2. So F2 is 0.81 times F1. And what is F1? We've gotten F1 before, the number of oscillation per minute. And it was what? 90. So 90 over 1 is 90. So definitely F2 is 0.81 times 90. So approximately we have what? We have 81. Approximately. Have 81. All right. That is that on that question.